Welcome back to Differential Calculus. In this video, I want to talk about inequalities and intervals. I am very confident that in your previous mathematics coursework, college algebra, pre-calculus, elementary functions, however it was called, you talked about the kinds of inequalities that I wanted to talk about today. You may or may not have talked about intervals, at least in the way that I want to. So let's start there. An interval is a connected portion of a number line. So if I sketch out a very quick number line and I select a set of numbers, a subset of the real numbers on this number line, if I choose all of my numbers in one region, that is an interval. I can represent an interval using a letter. How about I for this set? If I choose a couple of particular points, and I say that all four of these points together make up a set S, that set is not an interval. So in this particular example, it might be that S is the set that contains, say, the points 10, 15, 21, and 24. Distinct points, not connected, not an interval. I is a region. I can write I using set builder notation. It is the set of all x's in the real numbers such that maybe 0 is less than x is less than 5. Right? It's all of the real numbers inside this region. It is a connected set. It is an interval. When we talk about intervals, we can talk about them being bounded or unbounded. A bounded set has an upper bound that I'm representing as capital M and a lower bound, which I'm representing as lowercase m, such that little m is less than or equal to x is less than or equal to capital M for every x in my set, which I had to name S, and I forgot to name as I wrote the definition out. Right. This is true for any set, not just an interval. And an unbounded set is lacking an upper bound, a lower bound, or both. For my purposes in this course, I'm not worried about bounded or unbounded set classifications for things that are not intervals, but you can define that for any kind of set. And for anyone who continues onward as far as Calc 2, Sets which are not intervals will be described as bounded or unbounded in that course. And yes, it is possible to have an unbounded set which is not an interval. If you continue on to Calc 2, you'll play around with some ideas there. One of the interesting things about having a bounded set there's a lot of detail here that I'm not going to get into because it's not all that important for what we're doing. But a bounded set is closed if it contains an upper bound and a lower bound. That definition in and of itself is a little bit strange because one of the things that's easy to gloss over when you're talking about upper bounds and lower bounds is that there's more than one. Let's go back to my interval I, the set of all x's between 0 and 5. I can sketch this interval on a number line. I can sketch it pretty easily. It comes between 0 and 5. It does not include 0. There's a couple of different ways that you can denote that on a number line. My method of choice is to put a curved mark there, which indicates it comes close to but doesn't quite get to 0. And then the same thing at 5. I think it is pretty obvious that 0 is a lower bound for this interval. Every number in the interval is bigger than 0. One of the things that is not immediately apparent, but will be apparent if you think about it, -1 is also a lower bound for this interval. Likewise, 5 is an upper bound. 6 is also an upper bound. 12 million is an upper bound for this interval. Once you have a lower bound, there are infinitely many. Once you have an upper bound, there are infinitely many. But there is no upper bound which falls inside of the set. Any number that I pick smaller than 5 is not going to serve as an upper bound, right? 4.9 doesn't work because there's 4.99 and there's 4.999. If we try that, there's 4.9999999. We can always tack a couple more nines at the end of the number. So because this inequality is a strict inequality, this set does not contain its upper and lower bound. It is not closed. A set of real numbers is open if it does not contain an upper bound or a lower bound. This particular set is open, but I could modify it pretty easily to change that. All right. So let me just recopy the set we were just working on. The set of all x in the real numbers such that 0 is less than x is less than 5. That's the set we've been working on. And if I just duplicate that definition and modify it ever so slightly, to include 0 and 5, it goes from being an open set to being a closed set. But I could have done that a little bit differently. I didn't have to include both. I could have included just 0 but not 5. I could have included just 5 but not 0. If I do that, then the set is neither open nor closed, just to make things messy. All right, so sets can be open, sets can be closed. They don't have to be. Unlike some of the other things, every set is either bounded or unbounded. There is no other option. Every natural number is either even or odd. There is no other option. A set can be open. A set can be closed. A set can be neither. And just the fact that we have that third choice makes this a much messier thing than most of the properties that you've talked about in mathematics up until this point. Now that we have these ideas, it turns out that talking about intervals is so valuable that we created a new way of talking about sets known as interval notation. And I like to think of interval notation as being our best attempt at turning the graph of an interval on a number line into something we can type. Right, the open set, the open interval from A to B, the graph of it looks like this, the one we just saw for our interval from 0 to 5, where it comes close to but doesn't get to A, comes close to but doesn't get to B. We denote that with those rounded brackets. We use those same rounded brackets in the interval notation. This messes with people because that looks like an ordered pair. It has absolutely nothing to do with ordered pairs. It is completely different. It happens to use the same notation. Context will almost always tell you what's going on. Right? If we want to include those endpoints, I haven't drawn a graph that does this yet. But if I want to say that I want my interval to include the endpoints, then I will draw a square bracket when I graph this thing that solidly hits both of those endpoints. And again, I will use something like a square bracket when I write out the interval notation. Because we use the parentheses looking things whenever we're dealing with an open interval, and we use the square bracket looking things whenever we're dealing with a closed interval, you will often see the parenthesis in this context referred to as an open bracket and the square referred to as a closed bracket. You can mix and match. You're not stuck with one or the other. You can have the interval that is open on side A and closed on side B, or closed on A and open on B. Those are perfectly valid. And they do exactly what you think they would. Include one but not both of the endpoints in the inequality. But there's no reason that we can only use interval notation for a bounded interval. Most of the time when you're solving an inequality, you're going to end up with something that just has one side bounded. X is greater than or equal to 5. If I try to graph this inequality on a number line, I will start at 5. It includes 5, so I'll use a square bracket there. And then it continues onward without bound. It doesn't end. This is an unbounded interval. To represent the unbounded interval, well, the left-hand side is easy. It's got a square bracket, and that square bracket is sitting at 5. To the right is not quite so clear. And so the mathematics community invented an idea for this. We call that idea infinity. When I was first introduced to infinity, I was taught to write an infinity symbol, take your page, turn it sideways, and write the number 8. You couldn't see me doing it here, but I literally picked up my touch screen, I turned it sideways, and I wrote the number 8. Okay, I walked around to the side of the table so that I could write on it from the side, but I wrote a number 8 sideways. That's how you write an infinity symbol. Infinity is the upper bound of the real numbers. Infinity itself is not a real number. And that's why we always use an open bracket at infinity. Because the interval is talking about a set of real numbers. And infinity is not a real number, so infinity is not in the set. But every real number is smaller than infinity. That is the definition of infinity. We can also have a negative infinity going in the other direction. Negative infinity is the lower bound of the real numbers. It is not itself a member of the real numbers, so it cannot appear in any interval, but it does have that nice property of no matter what number you're looking at, it is smaller than it. So if I want x is less than 4, I can sketch that out on a number line real quick. Right, strictly less than, so parenthesis here, continuing onward to the left, continues indefinitely, and the interval notation here is going to go from negative infinity up to 4. For our purposes in this course, the value of interval notation is that it will allow us to write the solution set for an inequality. All right, so if I have, let's use a slightly bigger number, 27. 3 minus 2x is greater than or equal to 27. Solving this inequality, subtract 3 from both sides. Divide both sides by negative 2. Remember, whenever you multiply or divide an inequality by a negative number, it changes the direction of the inequality symbols. So I get that x is less than or equal to negative 12. I'm not going to require that you sketch out number lines when you're solving inequalities in this course, but I've always found it to be helpful, so I encourage you to do the same thing. We can write the solution set for this inequality as the interval from negative infinity to negative 12. One of the things that comes up quite a bit in calculus is working with three-piece inequalities. Negative 4 is less than or equal to x plus 5 is strictly less than 9. To solve this three-piece inequality, we have to act on all three sides instead of just the two sides. We want x by itself, so we're going to subtract 5 from each of the three sides of the inequality, which gives me that negative 9 is less than or equal to x is less than 4. Let's go ahead and sketch out that number line. And write the solution set in interval notation gives us from negative 9 to 4. One last example that I want to look at here is absolute value. And once again, I've talked about this a couple of times. There's a lot that can happen in an absolute value inequality, most of which I don't really care about. If you've studied absolute value inequalities in a previous course, you talked about convergent and divergent inequalities, inequalities that do and do not have solutions, all sorts of a mess. In this course, whenever we're dealing with an absolute value inequality, it is always going to involve the absolute value on the left and a less than symbol. And because of that, we can take a bunch of shortcuts. So the absolute value of something like 2x plus 3 is strictly less than 9. Again, I want to think about this as a distance. The distance between 2x and negative 3 is smaller than 9. And we know because of the way that absolute value works. I don't know if 2x plus 3 is positive or negative. If it is positive, then I just get back 2x plus 3. If it is negative, I would get back the opposite of 2x plus 3. I'm going to erase this, so probably don't copy it down just yet. So divide both sides of the inequality by negative 1 to get rid of that inequality symbol, and I get that 2x plus 3 is greater than negative 9. And so that's the idea I'm basing this on. Whenever I have an absolute value in an inequality and the absolute value is on the left and the inequality is less than or equal, either of those works, then you can rewrite this as a three-piece inequality. Negative 9 is less than 2x plus 3 is less than positive 9. If the absolute value was on the right, or if you did not have less than or equals, you'd have a mess, you'd have to do more work. This is not a course on algebra, I don't want to get into all of that. So there's a bunch of other stuff that can happen. You're not going to see it in this course. I don't want to spend too much time on it. Let's stick to the case that we do actually see. I'm running out of space, so I can't draw another graph here, but I can give you one last solution set in interval notation. This is the interval from -6 to +3. And that's what I want you to look at. I would like you to look at the inequality. The absolute value of 3x minus 5 is less than 7. Take a couple of minutes to work through solving this inequality and writing the solution set in interval notation. See what you can do with that one, and I'll see you in the next video.